Shall we start?
Let's start.
Okay. So the first thing I want to do now is to introduce some model. Just to make things very concrete, so what I want to do now is to discuss about how to derive hydrodynamic limits of interacting particle systems using this idea that I explained last time. Okay, so let me introduce a model which is called, well, people in the literature they call it the reaction diffusion model. Okay, so let me introduce some notation. So there is going to be a parameter n, which is a natural number. It's going to be our scaling parameter, and I'm going to think about these particles evolving in the discrete torus of size n. Okay, so in this discrete torus, we are going to think about it as a graph with nearest neighbor bonds. So I'm going to look at the particle systems evolving on this, and I'm going to assume that at each side there is at most one particle, which means that the space on which this, in fact, it's a finite state Markov chain evolves. It's simply 0, 1 to the lambda n. Okay, so it's a finite state, but very big. Let me introduce some more notation. I'm going to call B the set, the canonical bases. So this is the set of canonical vectors on lambda n, or Zn, Zd or Rd. Any of these spaces have the same canonical basis. So now let's talk about the dynamics. Okay. Okay, so actually it's easier to just explain you the dynamics in words, in a sense, so, or in drawings. So let me draw the dynamics instead of making more formal definitions. So these guys here are the particles. Okay, so particles means ones on this configuration space. So I'm going to call this side here x, this one x plus b, where b it's an element of this guy here. Okay, so here x belongs to lambda n, and b belongs to the set b. Okay, so this type of transition is going to happen at rate n squared times some function cxb of eta. Okay, so I'm already anticipating that I'm going to look at diffusive time scale, so I'm putting an n squared directly here. So this arrow goes in both ways, so it's a reversible rate. So this at this rate, the system goes from here to here, or from here to here. And this is, we think about this as a particle jumping to a neighboring side. Okay? So this is why I write x and x plus b, because these are actually all that describe all the neighbors on the.
So eta is the configuration?
Huh?
Eta is the whole configuration?
Eta is the whole configuration. Yes, this is. Let me write it here. Eta is a generic configuration on our space omega n of all the states. So, okay, just to give you one example. One possible choice of rates is this one here. Okay, so the choice C equals 1 is what is called in the literature the simple exclusion process, simple symmetric exclusion process. So yeah, they just the particles they just move around like simple random walks, conditioned to having at most one particle per cell. And here I add a little, I add some interaction. Okay, so here A is a constant which is bigger than minus 1/2, because we want this is a right, so it has to be positive. And well, actually, A equal to minus 1/2 is still not negative, but then it's going to be degenerated. We don't want it. So why I'm choosing this thing here is this is one possible interaction that satisfies what is called the gradient condition. Okay, I'm not going to enter too much into the details of the gradient condition. In a few minutes, just for simplicity, I'm going to take A equals 0. So it's just to put something a little bit more non-trivial as a base dynamic. So this is what is called the diffusion part. Okay. This is the diffusion part of this reaction diffusion model. So now I have to describe the reaction part. So the reaction part goes like this. So this means that particles can be created or annihilated in this model. Okay, so a particle disappears or appears with a rate.
With A positive, what is the invariant measure with this type of interaction?
It's a product because
it's product with
it's product.
It's reversible.
Yeah, because the point is that this guy here does not depend on x or x plus b. Okay, which is not going to be the case for the reaction part. Okay, so the rate for the reaction. Okay, let me call it R from reaction. And notice that there is no n square here. Okay, that is important if you want to in the limit get something in some hydrodynamic limit on which both parts of the dynamics play the same role. So just to give an example of rate R that one can take, here one can, there is no restriction basically on this rate. It could be whatever you want. Local is basically the only restriction you will need for what I want to present. So it's good to give an example. So the simplest non-trivial example is this one. So you may or may not recognize here the contact process. Okay, this is the rate at which particles are created or annihilated in the contact process. So in the contact process, you die with probability 1, with rate 1, and you, well, it's not dying. It's we call it you get healthy. So it's the opposite of dying, and then you get infected with rate lambda times the number of neighbors which are infected. Here I normalize by 2D because, well, the formulas look nicer with this normalization. And this is exactly what this rate is. Okay? And then this is, so this part here is what people call the reaction part. Okay, so if you plug these two dynamics together, you get a process that I'm going to call eta n dot and this is what is called the reaction diffusion model. Okay, so the actual reaction diffusion model is a sequence of Markov chains indexed by this parameter n, chosen in such a way that the diffusion part of the dynamics and the reaction part of the dynamics have the same weight, in a sense. Okay. So just since some of you in the audience have studied this kind of model, I had to talk a little bit about the literature and the references, and I don't have to, I will try to not forget anyone. So this model here, so when x is equal to 0, was studied by De Masi, Ferrari, and Leibowitz. But instead of considering a contact-like interaction, they consider an easing-like interaction. Okay, so what they did actually applies for any local interaction, as well as what we are going to do here. But now, well, it's a question about what example do you like the most? So this guy is like more the icing, and probably you also will like icing more because if you take icing like dynamics, the reaction diffusion equation is richer than if you take contact like, because contact like has two fixed points, one is stable and one unstable. But the easing like has also has three, no? One unstable and two stable. So it's more fun. But for the purpose of explaining what is going on, it's better to stick to that because well, I don't know if you can see it here, but this is those are the rays for easing like, which are more complicated. Okay. So you don't want to do that, at least for now. And they prove hydrodynamic limits. So they prove hydrodynamic limits and fluctuations around this hydrodynamic limit in the form of a CLP. So then also something which has been studied a lot is the large deviations. The large deviations principles for this kind of dynamics are very interesting because there is this reaction part that can be very complicated, especially if you have more than one stable fixed point. So then for the large deviations part, there are also works by the Bodinot, Lagouche, and Farfan, Nardin Sunoda. This is very recent. And so at the level of large deviations, what is complicated about this model is the case on which you have more than one stable fixed point for the reaction part. Then you will have metastability issues, and if you look at large deviations principles, that will reflect on the large deviation rates. Okay, so the other day I forgot to tell you about that. So what I'm talking about is based on this article on the archive, and so this is the full thing, and then there is a simpler version. That one on which we discuss exactly this model, but only in dimension 1. In case you want more details. So let's see. So what is the hydrodynamic limit of this model? So the hydrodynamic limit what does it mean? It means that density, I don't want to, for the moment, explain rigorously what does it mean hydrodynamic limit, because actually for each paper you have in the literature, you have one definition basically. Okay, because it's a vague concept that when you try to formalize, there are some subtleties, the model-dependent subtleties that make it a little bit annoying to formulate in a general way. So let's think about the density of particles converge, and that's the point. When you say converge, you have to explain on which sense it converges, because the density of particles is some sort of space-time field, and then you have to put topologies, etc. I don't want to do that. So this converges to solutions of the hydrodynamic equation, which is in this case is dvu equals Laplacian of u plus au squared plus f of u, where f of u it's something like it's u lambda minus 1 u. Be careful. That's correct. No, it's not correct. And it's u minus u minus 1. Okay, so this is the hydrodynamic equation of this model, and you see that in the hydrodynamic equation there is a diffusive part and a reaction part. Okay? So if you don't scale in this mixed way the diffusion and the reaction part, you won't get both. Okay? So that's why you put n squared on the diffusion part and you don't put anything on the reaction part. And this is easy to understand if you know about the spectral gap of Kawasaki versus Glauber dynamics, right? The Glauber dynamics equilibrates in times which are of order 1 with respect to the box. Maybe prove it can be difficult, but that's the intuition. And the Kawasaki dynamics on a box equilibrates in times of order the size of the box to the square. Okay, so if you want both to equilibrate more or less at the same time, you have to scale the dynamics later with n squared for the Kawasaki and with nothing for the Glauber part, or the reaction part. Okay, so another comment that one can see is that the diffusion part has a nice product invariant measure. So the Bernoulli product measures with a constant density are invariant for the diffusion part, but they are not invariant for the reaction part. Okay, that one can see that because the rate Rx, you see, it's when you have a hole, which the second expression is it's linear on the density, and when you have a particle, it's constant on the density, on the local density at least. So the data implies that you cannot have product invariant measures. So
Can you, I didn't hear what you said. Kawasaki equilibrates in what kind of time scale?
So it's the size of the box to the square.
Thanks.
Side length?
Yeah, side length. Yeah, I was reading an article today. They say no, they inaugurate so they open the biggest statue on the world, no? Which is twice the size of the Statue of Liberty. So what does it mean twice the size? It's the length, the area, the volume. So usually, so these guys at the newspaper they use the same convention as me. So it's the length. So now let me tell you what is the theorem we can prove, okay? Because all these people have their own proofs of hydrodynamic limit for this equation. So the first proof of these guys doesn't work for a different from 0. It's very important that a is equal to 0 for this one, but the other ones are very general. Okay, they work for a different from 0 as well. And then we also have our own proof. So in order to state it, the theorem, I need some definitions. So let me call. So here, so u is a space-time function. Okay, so I'm going to use u for the solution of this equation. I'm going to use u sub t for the solution of time t, and u dx for the value of this solution at times t and position x. So let me define the following measure. So regarding the discussion of last time, if you believe that the density of particles converges to the solution of this thing here, it also means that this measure here should be a good approximation of the dynamics of the law of the dynamics at time t. Okay? It will be, one could say, a zeroth order approximation or first order approximation of the law. So it makes sense to use it as a reference measure. Then we call that fnt was the density of the law of eta n t, and here this is with respect to the dn. Okay. And okay, and let me call h n of t the entropy. The relative entropy of ft and then what we can prove, and this is doing work with my student Otávio Menezes, is that so there exists a constant c that only depends on u, well, maybe it can depend on lambda and a. Okay, so it only depends on the parameters of the model and on the solution of your equation, of the equation we're choosing, such that h prime of n, so the derivative of the relative entropy is less or equal than a constant times the entropy plus n to the d minus 2 gdn, where gdn is equal to, so it's n equals 1 log n d equals 2 1 d bigger or equal than 3. Okay, so you may or may not recognize on these numbers the Green's function of the simple random walk on dimension d when you look at a domain of size n. Okay, so if you look at the so, well, of course, the random walk is recurrent in dimension d and 2, so d equals 1 and 2. So what you do, if you want to have something that works in any dimension, you look at the random walk and you kill it when you escape from a wall of size n. And then you have a well-defined Green's function, and these values here are actually the values of the Green's function up to constant at the origin. Okay? So, and this is actually why these constants appear here. That's exactly the reason. There's going to be some sort of random work later on. And so I claim that this theorem here is a version of the hydrodynamic limit. Okay. Why? Because so so if hn of 0 is less or equal to another constant times this factor, no, nd minus 2 gdn. So let's see. So in this factor here in dimension d equals 1 is equal to 1. It's in dimension 2 is log n, and in dimension 3 is d minus 2. So, well, if initially the entropy is smaller than this, then you have a bound like this. Just applying Romwell's inequality, you get this bound. Okay? So in particular, this thing here is uniformly in t over finite intervals of time t is uniformly bounded by this quantity n to d minus 2 gdn. Okay? Okay, so why this is a version of the hydrodynamic limit? Because you have the following corollary. Okay, so for any p smaller than 2, for any function f which is continuous on the torus of dimension d, the following is true. Okay, so you have this bound. The exact value of the constant there is not super important. The only the main point is this constant goes to 0 as n goes to 0. Okay, so which means that this random variable here converges to 0 in LP for any p smaller than 2. Okay, this is actually a simple consequence of this bound here, plus the entropy bounds for moments of functions. Okay, and what this function is doing, so you take a test function and you compute the integral of the density of particles with respect to this test function. So this is not probably this is even true. You don't need f to be continuous, but you put continuous there just to emphasize that you're thinking about the density of particles as a measure. So if it's a measure, it makes sense to test it against continuous functions. And this part here, no, the sum of f times u here converts to the integral of f times u. And this part here is the density of particles. So, so this means that as a measure, the density of particle it converges to a measure which has density u with respect to the Lebesgue measure. Okay, so this is what this corollary is telling you, and something which is it's a novelty on this business is this constant there, because this is a quantitative version of the hydrodynamic limit, and And this is already something new that was not present in the literature. Okay, so probably working a little bit harder with the Massey Ferrari-Leibowitz method, you can get some speed of convergence, but then it's the type of proof that they did is very restrictive in terms of the model you can consider. Okay, so this is the hydrodynamic limit.
So somehow, so T is fixed, or
T is fixed there.
T is any T fixed, because on the right hand side there will be bad constant in T, right?
It will be a bad constant in T. But it's bad, but not so bad in the sense that
It's exponential.
yeah, there is an exponential. So and it cannot be better than that. Okay, because so actually this is a good observation, because this theorem is true for the contact process and also for the kind of type of icing type of interaction on which you have more than one stable point. What does it mean to have more than one stable point? That you expect that in the limit you will have an invariant measure concentrated in two different densities. And if it's concentrated in two different densities, it cannot be close to a product measure. So it means that the entropy has to grow after the hydrodynamic limit. Okay? And after a little bit of juggling, you discover that it has to grow exponentially.
So somehow the hydrodynamic time scale is 1 in the normalization you chose, and if you go beyond that, then you have to
do something else. So that you have to describe your system in a different way.
what can one do then?
Okay, so this is still interesting thing, because there is this factor here which is like 1 over n, let's say. Okay, it's going to be 1 over n in dimension 3 or higher. But there is exponential guy, right? So that you have something like e to the t divided by n, which means that you can go up to times of order log n, right? Which it seems kind of modest, no? But if you look at this motion by mean curvature problem, okay, so you take a Gisborne-Landau type of potential, that scale is enough to be in that regime. Okay, so using this, you can prove this motion by mean curvature. That if you start with there is this phase segregation and things like that. Because this type of phase segregation is something that it still happens before you go to the mixture of two states with different density. So this is something which Funaki and Tsunoda are working on. It's not a completely new result in the sense that this was kind of known in the literature, but it seems that people didn't know how to do it in the nonlinear diffusion case. Okay, so the people knew how to do it if you put a linear diffusion plus these polynomials, these potentials, but not for nonlinear diffusion. So that will be the novelty in this case. Okay, but although the constant looks bad, it's still good enough to give you something interesting.
Are you going to explain how to go from the theorem to the corollary?
It's just entropy inequality. I'm going to write some entropy inequality later on, so maybe you can ask me again when I write it down. So now, how do you prove this kind of thing? So let us recall now a Gauss inequality. Okay, so Gauss inequality tells you how to bound this derivative there, no? In terms of some other stuff, okay? So in our case, Gauss inequality is going to have the following form. H prime of t is going to be smaller or equal than, so there is some constant here, so, well, all constants from now on are going to be generic, so. And very soon I'm going to start to drop all the n and t dependence on everything because it's kind of annoying writing them all the time. So Gauss inequality can be written as this. So there is a negative part which is I have to write. We'll write it down in a minute. And there is a positive part. So there was this Fisher information, and there was this entropy production term. Okay. So then, so the entropy production term is what? So for any function h, this dh of mu, so you take a function h and a measure mu. It was this guy here was the integral of the Carré-Duchamp of h with respect to the measure mu. That's what appeared in the Java theory. In our case, this is the following. So let me write it like this, because I want to use this notation later on. So I need to define that guy. So I hope the notation is a little bit self-explanatory. So what is going on is that so this nabla h plus b is the discrete gradient of the function h when you perform a jump between h and h plus b. Okay, so and this is the configuration you obtain by exchanging h and h plus b. So it is here, no? When you do this, you get this difference on the function f. And this is the so-called Carré-Duchamp. It's not exactly the Carré-Duchamp that you get from this model, but aside from constants, is this thing here. And I'm taking away, I'm throwing away the reaction part because it's not going to be useful for us in this setting. In other settings, it could be useful. Okay, so in particular, if you want to improve this, so you're really worried about this exponential constant there. You can improve the exponential constant there to making a final analysis of what happened with the reaction part. If the reaction part helps you, then you can get a little some little bit better bounds. So so this is this part here, and then the function f. So the function f, okay. I'm going to save you from the computations, which are very.
So what is the time scale up to when the hydrodynamic limit is supposed to be good description? So you said it's bigger than at least log n, but
Yeah, it's the fastest you can go. So you expect that because of the of this combination of Glauber and okay, so let me see how I want to say this. Okay, so for the Kawasaki part, you expect that it mixes in times of order n squared log n, and the Glauber part 2. So you expect that everything just equilibrates at the scale log n in this hydrodynamic picture. Okay, so the hydrodynamic picture should be good until a little bit before that. Okay, so everything gets flat and then you mix. So now the function f, you have to compute it. It's a long but elementary computation, and so if a is equal to 0, you can write it in the following way. Okay. What is it? You can write it like that, okay? Okay, so the function f can be written like this. Okay, so there is this product of two occupation variables centered. So these two guys are centered and independent in this case, but what is important is that there are different sides. There is a function g here which is bounded, and is bounded with respect to everything. So n, t, and x, because the x is inside the supremo. And omega is this function here. Okay, so it's a centered occupation variable. So the occupation variable is equal to 1 or 0, depending on whether there is a particle or whole at position x, and normalized by this constant there. That for some reason it keeps popping out, and it's good to define it like that because it simplifies the expressions. And so
What did you
here,
say, sorry, what did you say? UX is?
ux is this u here.
Oh, okay.
Okay, so actually it's u of t, comma x divided by n. But, okay, it's a little bit annoying to write all of that. So here I took a reaction term with a quadratic type of interaction. That means that here you will have product of two guys. If you take here a cubic type of interaction, here you will have a product of and this is for a equals 0. So if a is different from 0 here, then this is going to produce here a term of 3 guys too. Okay, but what is important is that in this expression here you only have monomials of degree 2 or higher. Okay, so this is here I have to put lower order terms, but the point is that so if you just choose a product measure as your reference measure and you do the computations, here you will get some terms of order 1, in the sense that they are linear on the variables omega x. How do you kill those terms? Imposing that the function u satisfies the hydrodynamic equation. So in a sense, this is what fixes the limiting equation. You just want to kill the linear term on this expression. So you have something quadratic. And the idea is that something quadratic is much better behaved than something linear. Because at least in a diffusive system, the density of particles is conserved, which means that the density of particles is the quantity that takes the most time to equilibrate. And if you take something which is not the density of particles, like averages of these products things, they should equilibrate much faster. And the point is that they don't equilibrate much faster in the sense that they equilibrate maybe a little bit after, a little bit before. They really equilibrate way before. Okay? And yes,
usually to get this to remove the linear part, I mean it's quite a lot of work. Do you have like a systematic way to see it, or you have to do it equation per equation?
So I do have a systematic way that I never wrote down because it's still annoying. But I mean, if you do it like, what is important here is this gradient condition. Okay? And but in principle you can let's say there is a systematic way to do it, but then what is going to happen is that this U will satisfy some equation, which is a discrete equation, and then you have to ask your favorite friend in numerical analysis to discover where this numeric scheme converges. Okay, and actually these guys in numerical analysis, they have systematic ways to tell you where these kind of systems converge. Okay, so
So does that mean you would actually have a better result if you wrote U is actually the solution of some difference equation?
yes and no. So in this particular case, no. In other cases, yes. Because in this particular case, what happens is that the solution is very smooth.
Yeah, sure.
Okay. So if the solution is not smooth, like it has shocks or things like that, maybe, or it's or have this kind of, for example, it's a porous medium equation which has boundaries, etc. Then you have to be very careful about what you put here, and then it's very useful to put there the right discretizations instead of.
But you were saying kind of if you put the discrete term, you would have fewer error terms. It's just because error terms are tiny.
Exactly. So if you put the discrete guy, instead of having lots of terms, you have
Slightly
less terms.
Okay. But I mean, that would suggest you perhaps do it as post-processing to just prove your statement with the discrete equation and then post-process the numerical analysis question.
Yeah. So yeah, for some reason, this is something I never quite understood. That these particle systems they have this tendency to choose the right numerical discretization of your equations. In some sense, they are the best. They do the best they can. I mean, they don't do better than numerical analysis because, okay, a guy in numerical analysis will immediately tell you why don't you use, I don't know, Runge-Kutta or Crank-Williamson or whatever other much better method. I just, I have a particle system. I cannot just change my particle system to something non-Markovian because you want Runge-Kutta. Anyway, so now, well, this is just what tells you the Gauss inequality. And so Gauss relative entropy method is a way to tell you that this expectation here divided by n to the d converges to 0. Okay? So, but I want to do better because you see in dimension 3, for example, I have n to the d minus 2 as a bound. So I want to, that is 1 over n squared better than Gauss bound. The usual that is in the textbooks and is being used for deriving this equation for the last 20-25 years. So if you want to do better, you have to do something else. And you want I introduce what I call what is that? So yeah, for the main lemma. So everything I've done up to here is kind of well known in the interacting particle system business. But now there is something new, which is the following. So there exists a constant. So now so now our task is to bound this guy, no, this guy, no, the expectation of this guy, in terms of this negative term here. Okay, because this negative term here should pushing things down, so you have to make use of that. So what you want to do is to take advantage of that. So there is a constant that depends on g, only on this norm here, and on the function u, such that the integral of x and b of the sum of exactly that guy that I got there this is smaller or equal than, so such that for any delta bigger than 0, and for any f okay, so what I'm saying is that, well, I just told you, no, I want to bound this guy in terms of this guy, and the main lemma tells you that you can do that with a cost, which is exactly what appears on the theorem. So if you assume this lemma here, then the theorem is kind of immediate, okay, because you just choose delta equal to 1 or 1/2 maybe, because maybe you have to use it twice, this lemma, and then you kill the negative part here, and what is left is exactly the right hand side of the inequality you get there. Okay, so what you want to prove is this, and this measure mu here is this product measure that you constructed using u. Okay, so well, I still haven't said anything really striking yet, because of course, I mean, I told you, well, you want to bound this by this, and lemma, you can bound this by this. Now you have to say something more more interesting, and now I'm going to focus on this lemma. So
mu is mu n, right?
yeah, so yes, but the point is that this lemma here does not depend on the fact that there is an n there. No? I mean, it's you take any function u if you want. It doesn't have to be a function that depends on time. It doesn't have to be the solution of some equation. Just take some profile u that you like for some reason, and then you start to estimate these things here. Okay, so if you know some nice properties of this measure mu, for example, you know inequalities like the spectral gap inequality or the log overlap inequality for this measure, for this quadratic form with respect to this measure here, you can prove this thing here more or less easily. Maybe with not the right, maybe not the right exponent there, but the point that I want to make now is that this is a little bit of overshooting, okay? Because using this strategy, you are filtering out the modes that equilibrate slowest. Okay, so this guy should equilibrate faster, and then you say, okay, I'm going to use something that I know about how these guys equilibrate in the worst case scenario, and then I can prove my theorem. And this is, I mean, you're not really using the fact that you already filtered out the worst case scenario. Okay, so, and this is it seems that this is the new idea that allow us to go much further than what people did before. Okay, so now I want to discuss some of the ideas of the proof, and as usual, I mean, if you want to write down a proof, you do it. You always write it in the inverse way. No, you start. Oh, let's do these very clever definitions, and let's go from here down there, and then you get a very elegant and comprehensible proof. So what I'm going to try to do now is the opposite way. So I'm going to explain you some things which are kind of vague, somehow, just to give you an idea of how one can think about this. Okay? So the first observations is that, okay, so I want to bound expectation of functions in terms of this guy here. This guy here has inside some squares. Okay, so there is a well, there is this gradient of f. Actually, the square root of f, that's a little bit annoying, but not too much. So for simplicity, I'm going to assume that u is spatially constant. Okay. This is still meaningful in the constant because so it's a reaction diffusion equation. Okay, so it has some critical point, and maybe you start with a constant density, but which is not the stable one. So then this reaction diffusion equation gets reduced to an ODE, which density goes to the critical one, but you still have something to prove. No, you still there is still something meaningful to be done, and it turns out that it's not too much easier to do that case than the general case. So, for simplicity, I'm going to tell you how do you proceed in this case, okay? Which, in other contexts, also it's not so naive to do. Okay, so I will start doing some positions here. But I'm going to start with something very nice. So I want, in general, I mean, if you want to estimate some integral by this guy square, this is the easiest thing you can estimate because you can just Cauchy-Schwarz it, no? But okay, there is a square root there, so it's a little bit annoying. If it were a diffusion, it will be less annoying because you have to rewrite this as the following. You write it like this, and now you do some Cauchy-Schwarz with weights to put in evidence the nice part. And now you have the square of this guy on the other side, on the right hand side. Okay, so you have h squared and the square, and there is a square root here that I forgot. Okay, so you get this squared, and so the square of the sum is smaller than twice the sum of the squares, something like that. So and here you get something like f eta x plus b plus f of z. Okay, and this guy here is equal to 1 over beta, the integral of h squared. So you undo you pass this flipping of particles to the function h, because actually the measure here is invariant under this flipping. It's at this point where you will get something different if the measure were not invariant. But the point is that the function u is smooth, so the error you commit is not so big. Okay, so you start with that. Okay, that doesn't seem very. It doesn't seem very very deep. But the point is that we will discover something about the system by doing this computation. So, okay, so this is not still a way to bound functions that depends on to bound integrals of the form h times f, because the gradient is on the wrong side. Okay, so now you can undo this thing here. You can pass this gradient to a function h. Okay, because this operator is actually antisymmetric with respect to the measure mu. Okay, so this is actually equals to minus sx plus b h f d. Okay, so what does it mean? It means that so this is some version of what some kinds of people in PhDs call an energy estimate, no? That somehow you can estimate gradients by L2 norms. So this is one version of that. But of course, the function that I want to estimate is not a gradient. So this is going to pop up in a minute. So, for example, so what this computation tells you is that this integral here can be estimated by the quadratic form that I have in my estimate with the negative sign, plus some error which depends on the L2 norm of the function. Okay, so it is really like an integration by parts formula. So let me do an example. So the example I'm going to take is the function h is going to be equal to g times omega x. I'm going to assume that the g is left invariant under this change here. Okay, so it means that when you take this gradient of h, the gradient does not affect g. Okay, so if you trace back all these inequalities there, what you discover is this bound here. Okay, so, and this is true for any beta. This is true for any beta. So in particular, it's true for beta equals to delta n squared. Okay, and there is a constant here because there you have h squared plus switch it plus times h squared, and when you switch it, g is not changed, but you change wx to wx plus b. So you have actually the square of these two random variables, and that's something bounded, and you have to solve it in this constancy here. Yes?
When you change omega x, the u is not changed. So does it lead to a small?
Yeah, yes, but this is why I'm assuming, I mean, for simplicity, that the U is especially uniform.
Okay.
Okay, if it's not especially uniform, you make a mistake. Okay, but since most of the audience here is expert in RG methods, they probably can you can probably figure out that if I can do U constant, then I can do U non-constant by a renormalization procedure. Okay, actually this is something you can do. Because the error is going to be smaller, but it's going to be of the same class, and then you repeat and repeat and repeat until you win. So what does this bound actually is it's very interesting, because what it's telling you is that I know how to estimate things that have gradients somehow. Okay, so if I can rewrite my function as sums of gradients, then I'm in good shape. Okay, and this computation here also, when you take a more general model, it will tell you which kind of functions are the ones that can be estimated in this way. So it means whatever it appears here is a type of function which equilibrates much faster than the density of particles. So these type of functions that can express in this way, they have somehow a sort of local equilibration system that makes them equilibrate much faster than the whole chain. So here you're really doing this computation, you discover which are the functions that equilibrate faster, but orders of magnitude faster, not just a little bit faster. And then you cross your fingers to make them a set of functions rich enough to be able to handle the one I started with. Okay. So the one I started with does not have these gradients, no? So you want to manufacture them somehow, okay? And from the experience in what we have in hydrodynamic limits, we kind of know what to do, okay? So, okay, let me do some definitions to make notation slightly simpler. There, the sum over B, you can ignore it because there are D possible choices for B, and if you handle one, you handle the other one. So let me write this. Okay, and let me define now an homogenized version of this guy here. Okay, so this guy here, QL, is a measure on lambda L, okay? Lambda L, well, it's not the torus of size L. In this case, it's just the cube of size L, okay? And this is a measure. So this is kind of a homogeneous version of it. And one possibility which is you can do is just to take Q as the uniform measure, okay? Sometimes it's better not to do that, because maybe if you know a little bit about discrete Fourier analysis, you know that making uniform measures on boxes is not good. It's better to do, for example, you convolute two uniform measures, and you get something like you know, it's spline shaped, and that guy for Fourier analysis is much better, because the Fourier transform doesn't oscillate. It's not the Fourier transform of that guy is positive, but the Fourier transform of the of the uniform measure is a oscillating thing. Okay, so maybe you want to put there something which is better than the uniform measure. But anyway, at the end it doesn't matter. Yes.
It should be omega x plus z would be.
Yes, of course. Thank you very much. Otherwise, I'm not doing anything. No? And so, from the experience with having hydrodynamic limits, we know that okay, this is kind of local function, and you want to express it in terms of a function of the density of particles. This is like the density of particles somehow. It's not exactly the density of particles, but it looks like the density of particles. So now, let me define the following thing. So let me introduce this guy here. Phi L is a flow from delta 0 to QL. Okay, so what is a flow? So we have our square, and on the square you have edges, and a flow is a function that is defined on the edges, such that so you start with mass delta 0, which is with mass 1 at 0, and you look at your edges, and those edges tell you how to distribute this mass. Okay, so you start at 0, you imagine that you are at the corner of the square, and you have two directions, and then you split. And now you split again. And you keep going. Okay? And you say that a flow connects two measures if the final result of this procedure is the second measure when you start. Okay? And so you have to define a flow. It turns out that there are various ways to define flows.
So you want the divergence of the flow to be equal.
Exactly.
To yeah.
Exactly. So this is so I didn't want to say it like that, but it's actually, it says exactly the property that we want to have. That the divergence of the flow is the difference of these two. Which means that the difference of these two guys, I can write it in terms of this guy here. Okay? So that implies that actually omega x plus b minus omega x plus b L is equal to the sum over z and b. So one possible way to parameterize this flow is by z and b, no? Because this is a way to parameterize the edges. And now you will have something like x plus b plus z minus x plus b plus z plus b. Two b. So b prime, b prime. Okay? So in this way, you can write this difference as sum of gradients. And then it's good, sums of gradients, and then I have a gradient here. So it turns out that to construct this flow, well, you can construct it by hand, maybe, or you can use some probabilistic argument to do it. Okay. So actually, on these articles, we have constructions by hand, because actually it turned out to be easier. Maybe if you know something about optimal transport, then you can do a more analytical construction. But the idea is that what this flow is going to be is like the green function somehow. No? Because you can construct these flows using some minimization problem, and if you minimize the L2 norm of the flow, what you will get is the gradient of the solution of the Laplace equation. So in that way, you can argue that the L2 norm of this guy here is going to be exactly the constant that appeared up there, which is the value of the green function at 0. Okay, so now that you wrote that, you can rewrite this difference as, so you plug this inside here. So you will have a sum over x z and b of these gradients times this flow times this function g times this function omega. Okay, you can do a change of variables on the sums to make appear flows here in because if you are going to use this inequality, it's better to collect all the same appearances of the gradients in just one piece. Okay, so you can do that doing the following. Well, you have to be careful with the maybe it's a bit. You can do that. Okay, so if you just plug this thing here, this sum here, into these two sums, okay, into the difference of these two sums, and you make a change of variables between x and z, you get this, and this is your nice gradient, and this is the function g. So I'm going to give a name to that. So it's going to be called g. So it depends on x, it depends on b prime, it depends on L, and also depends on the test function g. So it has a lot of dependence. But it's a function, okay? So it is a function which is, so the support of these guys here is the square behind this edge there, okay? So in particular, it's a function which is satisfies this property. Okay, you can verify all of that, and then you can use the lemma. Okay. So now you use the lemma, and you will get a little bit messy computation, but so these edges here appear exactly once on the sum because I reparameterize the sum in such a way that this difference appears only once, which means that this term is going to appear only once, and then I'm going to add, and when I add, I get the d, which is written there. So this is delta n squared d of square root of f plus a constant that does not depend. It depends on u, okay? Because this constant bounds the function omega, and the function omega has a u below, so it depends on u. And there you have the integral of the sum over x and b prime of these g's of x, L, g, b prime, square, f. Okay? So this is, all these computations are really messy, but they're not so complicated, okay? Everything is kind of elementary, but very, very messy. So, what does it mean? Okay, so it means that I can replace my original function by something with an average paying this cost plus this cost. And now, let's see how far can you go in here. Okay? So now, this is always a problem because there are like 100 different inequalities in the literature that are called the entropy inequality. So when you say, okay, I'm going to use the entropy inequality, you have to which one of the 100 ones you want to use. So I'm going to use the following. So this is a general thing. For any function h, this integral is bounded by this. Something nice about the fact that we are working with finite state Markov chains is that I don't have to worry at all about the integrability issues. Okay? So if you want to do diffusions, then you have to worry about integrability issues, but then you have also differential calculus to help you with that. So one thing or the other. So this is the entropy inequality I'm going to use. Okay, so this is true for any, function f, and for any density f, for any constant gamma bigger than 0, and for any function, for any u. Okay, so if I use
Just Jensen, right?
yeah, it's just Jensen, yes, of course. I know. But it's Jensen with x log x and it's Legendre transform, no? So, yeah, I mean, of course, I mean, if you do large deviations, you know all this stuff, or statistical mechanics, etc. But anyway. So those are the two possibilities. Either people say, Jensen, or how do you put that? Because either you see it or not before, no? Anyway, now you use this up there to get a bound, because so the main lemma tells you that you can estimate this integral by a piece which is this quadratic form plus another piece which is the entropy. And of course, it looks very much tailor-made for this, no? And so then you see that 1 over n squared, the integral of this sum. Okay, so now my time is almost over and I really want to end this computation, so I'm going to do it very quickly. So this is less or equal than 1 over gamma n squared. So you have the entropy plus the log of the exponential of that thing there. Okay, so here I have n to the d terms. Okay, so since the measure is product, maybe I have an n to the d here. Okay, but these functions here are not independent because they have a support of size L. So how do you get rid of that? Using a holder. And if you do holder, you discover that there is an L to the d here, because there is an exponent L to the d on the holder, which when you take the log, goes down here. This seems too good to be true, and it is too good to be true because what happens is that the L to the d goes up to the exponential. Here you have something gx. Okay, and here, of course, I forgot there is a max over x. Okay, because this will kick you out n to the d terms, and then you have the sum of this n to the d terms, which is bounded by the number of terms times the max. Okay, and now so the observation we can do is that this function gxl is sub Gaussian. Okay, what is the definition of is there? So you see, it's a sum of independent random variables. Therefore, by your favorite concentration inequality, you know that it has Gaussian tails. Okay, so if sub Gaussian of order. So what do I mean by the order? It has tails which are bounded by a Gaussian, but by a Gaussian of some variance, and the order is the variance of that Gaussian, which is basically a constant times the variance that is of this guy there, which is g infinity squared. Okay, so I just bounded the function g by its maximum, and then I have the L2 norm of phi L, which is equal to this constant GD that I defined before. Okay, so now what does it mean? It means here I'm taking the expectation and there is a square here that I forgot, which is important, of the square of a Gaussian. It means that it is small if the prefactor is smaller than 1/4 or 1/8, something which is a fixed factor times this guy here. Okay, so if you plug everything together, you get now that you can choose gamma minus 1 equal to LD times this, so you get something of the following form. So you get a constant times G infinity squared times L to the D times GDL divided by n squared times H plus L to the D, L to the D. Okay? And now what is the best choice for L here? So if you optimize on L, you discover that you have to take L equals to 1/8 in D equals 1, n divided by square root of log n, and D equals 2, and n to the 2 over D, in D equal to 1. So these are your choices.
So it's finite in one dimension.
Sorry, n divided by 8. Oh, the opposite of finite. Okay, of course, n divided by 8 is just because it can be of order n, but you have to make some room because you don't want these intervals to go around the circle.
So it means that what you've been doing is like the 1 and the 2 block estimate in one go.
Exactly. In one go and without compactness, very explicit. I mean, this is very explicit computation. And once you do this, you can check that the bound you get is exactly this one here. Because this, so what happens when you choose L like this prefactor is equal to 1. And then you get ND divided by L to the D, and LD is exactly this ND to minus 2. So this is one half of the argument. The other half of the argument is to bound now VL. So VL now is a sum of two things. It has this omega L and this omega X plus B. But now you can do the same thing with the omega X to the other side. Right? You can also change the omega X by its average. Because, well, if you do it once, you can do it twice. And then, if you do it twice, you again get something which is like a square of a Gaussian. You do the same computation and you get the same bound. So, at this precise scale here of L, VL and this error term here have exactly the same order. So, so basically that's the proof of the main lemma, and with this main lemma you prove this entropy inequality. And so, what are the message that I wanted to pass is that what I used here is that first I discovered using this integration by parts arguments, not very complicated thing. I discovered first what are the functions which I can estimate easily. So the interpretation of that is those are the functions that equilibrate very fast. Now that I know which functions equilibrate very fast, I go to the function that I want to compute, which probably is not one of those, because if it were one of those, the system will be super mixing. It's not usually the case. But what happens is that using these functions that equilibrate fast, I can introduce space average on the original function. And once I introduce the space averages, now it becomes a large scale problem, and on this large scale you the dynamics already plays its part. Okay, so that was to equilibrate things and make all functions look like the functions of the density. And once you do that, well, you get some bounds, and hopefully you get the correct bounds. So last comment, and now it's really the last comment, is that this estimate is sharp. You cannot do better than this. You cannot do better than this factor n to the minus 2. Okay? Because, well, there are various heuristic ways to claim that, but there are some something I actually prove. I think you did something like that in this article you mentioned before. How the invariant measure should look like for this model? It should look like a combination of the white noise, which is the invariant for diffusion, and free field, which is the invariant for the reaction. Okay, so it's white noise plus free field. Free field and white noise are not continuous one with respect to the other, except in dimension 1. So in dimension 1, this bound, that the bound is independent on D is okay, because it means exactly, it exactly means that. In higher dimension, they are not absolutely continuous with respect to the other, but here we're doing some sort of ultraviolet cutoff, no? Doing it on the lattice. So it's like taking averages of the continuous or for the 1 over n or something like that. And if you do that, now you get, when you do that with the free field, now you get something that it's absolutely continuous with respect to white noise. Not the free field, but white noise plus free field. Okay? And if you compute the relative entropy of these two guys, is n to the d minus 2. So, and here we're looking at a time window on which you already create that effect, a little bit at least. So because you can go to times which are very, very big, and for the continuous equation, those big times, for those times of that order, you already are close to the invariant measure. So you really expect that at fixed time t but large, this picture I just mentioned is already true. And this is and even if you don't have the reaction part, this heuristic is still true, because if you don't have reaction part but you have a profile which is not uniform, what you see locally it's a diffusive driven system, because the density is not uniform. So the gradient of the density is driven the system. And in diffusive driven system, the same picture appears. You also have that invariant measure is a combination of white noise and free field. And therefore, the same argument tells you that the entropy cannot be better than n to the d minus 2. Okay? Okay, now